What are we learning?
Section 4.1, we are learning something called Antiderivatives. Okay, so we know how to do, okay, calm down just a little bit. I know you're super excited. I know you guys know how to do derivatives. That's what we've been working on for a couple months now, right? Are y'all with me?
Yes.
There's a lot of talking going on. Okay, here's what I'd like for you to do first. You have an entire front sheet of your notes that says derivative rules. And I need you to fill in all of the derivative rules that you remember. If there's pieces of them that you don't remember, now is probably the time to be concerned and to remember them for Friday. Okay, but fill in what you do remember from the derivative rules. The entire front sheet is what you're looking to fill in. On the middle it says function, and then over on the right hand side it says derivative. So you're going to fill in the right hand side. So you've got constant rule, it says y equals b. What's the derivative of y equal b? Linear function rule, you've got a function y equals ax plus b. What's the derivative of that? So you're just filling in the derivatives as you go down the right hand side. This is the first, I don't know, 6 of them or 5 of them or something. 5. So fill in all of the derivatives on the front side of this piece of paper. Okay, so we're going to go down this list, and once you give me an answer, you need to be quiet and let somebody else give a different answer, okay? That way everybody gets to participate, unless you're scared to talk to me. I'm not going to make you participate out loud, but... All right, so somebody tell me what the constant rule's derivative is. Okay, so we'll go over this side. Y prime equals 0. So now Garrett gave me an answer. Did everybody get y prime is 0?
Yay.
Oh, that's so good. All right, someone else on the linear function rule. Luke, I can tell you're dying to tell me something. What is this one?
Honestly, I feel like I'm getting it wrong, but I just put A.
Yeah, you're right. It's just A. Remember, linear functions is, I should say, remember derivatives are just slopes, and the slope of a linear function is just the slope of the equation because it's a line, so it's A. All right, constant multiplier rule. This is one of those ones where we use it all the time, but when we write it down, it feels a little bit funny just because we don't think about it that way any longer. So somebody tell me what you think this one is.
K times the derivative of x plus the derivative of k times.
Yeah, and the derivative of k would actually be 0 since it's a constant, so we don't have to write that part of it. Yeah, so it simplifies even further. So this is just k times the derivative of whatever the variable part is. Okay? Yeah, so even simpler. How about the sum difference rule? Who remembers that one? All right, Fallon.
Okay, the sum is f of x times g prime of x plus g of x times f prime of x.
You're thinking about the product rule. This one's just sum.
Okay, then it's
Okay.
just f prime of x plus g.
Right. And we have a plus or a minus here, so I'm going to write mine with a plus or a minus between them because either sign would be the same rule. Okay, how about power rule?
Y derivative is equal to the n x to the n minus 1.
Okay, so we bring the exponent down and then we decrease the exponent by 1. Okay, is everybody good with this list so far? I think what we have left are the trig rules, right? They're our favorite. All right, what's the derivative of sine? Somebody who hasn't talked to me.
Cosine.
Cosine. Okay, Dawson got his,
Forgot x.
Yeah, cosine of x, that's true. How about the derivative of cosine? Negative sign. I heard Kinsey. Thank you, Kinsey. And I heard somebody else too. Who spoke? Gus? Is that one you? Fabulous. Okay. Those are the ones that we tend to remember the easiest just because they go back and forth. The next ones come in pairs. So I tend to think of these two coming sort of in pairs together. I didn't mean that. I totally didn't mean that at all. This one and this one come in pairs. They're just in your list of your book. Or what's the derivative of tangent?
I kind of think the other two.
Do you?
Yeah.
Okay. Well, that's fine. Let's just go in order, but...
Go together in my mind.
Okay, because they've got each other in them. That makes sense, too. What's the derivative of tangent?
Secant squared.
Secant squared.
Good job, Gary.
All right. And the derivative of secant? Secant x tangent x. Excellent. Two more left. What's the derivative of cotangent? You guys are remembering these well. Negative cosecant squared. Very good. And the derivative of cosecant? Very good. And one of the things that, just as a reminder, on positives and negatives, this works for derivatives. All of the co-functions, derivatives are negative, right? Cosine, cotangent, and cosecant all become negative when we take their derivatives. Okay, what we're going to do next is we're going to go backward. So, what you're wanting to think about is you're wanting to think about if I know this function, y equals 0, is a derivative of something, what is it the derivative of? A number, right? I would have had to have a number to get a derivative that was 0. So we're going backwards, and what we do when we go backwards is that we actually change the lowercase letters to capitals, okay? So in antiderivative notation, we'll have a capital Y. We'll also see them more often like with a lowercase f of x, right? So little f of x equals 0, and we would use capital F of x over here on our antiderivatives, all right? All right, now there is a condition, all right, and I heard Mooney already say it. This is a constant. You can call a constant C, K. Those are your two that we normally use. I'm going to call it C, and partly because I've got a K in the next problem. If I took a derivative and I got K, what would the original function have had to be? Kx. And it could have a plus C on it, right?
Yeah.
Because the derivative of plus C would be 0. So as we work through these, every single one is going to have a plus C on it because it could be there and its derivative would be 0 and it doesn't show up in the derivative formula, right? So everything's going to have a plus C on it. What do you think? I'm sorry, somebody asked a question. Yes, these are going to all be capital Y's all the way down. All right, so let's see, constant multiplier rule. What do you suppose is going to happen when we have K times f of x? Just guess. What do you think? Yeah, do you think it's going to be plain old? I didn't mean that. I'm going to get K first. You're thinking right. How would I have to change it for it to actually make sense to be the antiderivative?
K divided by n.
Okay, so in our rule over here, you'll notice the relationship from the left to the right has a prime on it, right? So when I take the derivative, I get a prime. What I had told you over here is that the likewise sort of opposite notation here is that lowercase become capital. So this would be a capital F of x. Right now it just looks like a bunch of notation.
Yeah.
But we're about to get to some that actually look a little bit more helpful. Yes, thank you, plus C. Didn't get that on there just yet. So if I've got the lowercase f and the lowercase g with addition and subtraction, what do you suppose is going to happen? They're going to be uppercase capitals. So I got capital F of x plus or minus capital G of x, and then plus my c. And then now we're actually ready to figure out what an antiderivative of something really is. So far this all just looks like fancy notation, with the exception of maybe the 0 and the constant rule. But those last two just feel like all I did was change lowercase to capital. That doesn't really tell me what's going on. You guys with me? So power rule is our first one, and it is our dominant one. Think about what we did when we took a derivative. We took the current exponent and we pulled it down as a product, right? Well, what's the opposite of a product? Division. So we're going to see division happening here in a minute. The opposite of multiplication is division. Instead of using the current power, we're going to use the new power here in a minute. So we're going to be using a new power for this. How did the power change when I took derivatives? It went down by 1, and the opposite of that would be going up by 1. So what we're going to see happen is we're going to see the exponent increase by 1. We're going to divide by the new exponent, and it is division. Okay, so division instead of multiplication, new exponent instead of old exponent, plus a c on the end. Very good. That's the biggest thing that we're going to learn today right there. Okay? The opposite of the power rule is the biggest difference when we're doing derivatives. And then, of course, you can see that that's going to apply, hang on, that's going to apply in each of these locations right here, right? Because it will often have power rules or versions of them inside of the actual derivatives, correct? The original functions, which are now what the previous derivatives would have been. All right, the next set are our trig functions. So we have to think backwards. How would I have gotten a derivative that was sine? It would have been a cosine, cosine, and cosine switch, and it's the opposite sign because the derivative of cosine is negative sine. So if you sort of think about starting right here and then taking its derivative, what's the derivative of cosine? Negative sine. But I want it to be positive, so I'm going to have an extra negative involved in the problem. So this is negative cosine, and of course I need a plus c. What's the derivative, or what gives me a derivative of cosine? That would be sine. The derivative of sine is cosine. And I've totally done terrible notation already. What did I screw up? I didn't put capital Y's. Let me put those in. I got my plus C's, but I didn't put my capital Y's. Yep, I agree. Capital Y's just look weird to me when I write them, but that's okay. All right. You know what? I won't have to remember if I just do them all right now, right? You guys too. Put them all in there. Okay. The next 4 kind of look like ones you've seen before. Whose derivative was secant squared? What was it? Tangent. That's right. So this is tangent x plus c. Whose derivative is secant tangent? Secant. Secant x plus c. Whose derivative is cosecant squared? Yeah, it's the cotangent, and you'll remember that it changed signs, or it should have been a negative cosecant, and I don't have the negative, so I've got a negative here, and this is cotangent x plus c. And then whose derivative is cosecant cotangent? Cosecant, and again, I need a negative because I'm missing it, if you will, from the derivative part originally. What do you not see on this slide that maybe you expected you would? What was it? I don't see a product rule. We don't see the quotient rule. I don't see a chain rule. There's something else I don't see on this slide in particular with the trig.
Tangent.
I don't see the original function for tangent, cotangent, secant, or cosecant. Right? The one in the middle where it says function, that line, only has the ones that I sort of already know. You guys with me? And the reason you don't see that, like I don't see in the middle here, so you're like, I don't know what you're talking about. You don't have this written down. Correct?
Yes.
Or secant, or cosecant, or cotangent. It's not the derivative of something we've already encountered, correct? And here's the cool thing. You don't have to do it until after Christmas, because it's inside of Calc 2. All right? Yes, so you do not do that until Calc 2, Chapter 5. Yeah, all that trig stuff will come back up in Calc 2, but you don't have to do it for the rest of this year, okay?
I don't like it.
Fair enough? Okay. So what we're going to do now is we're going to find some antiderivatives. We're actually going to practice doing this, so to speak. The first one here is a 2x. So you can either think to yourself, there's 2 options when you encounter something that's linear. You can, well, not even linear, but that we're doing antiderivatives. You can think to yourself, what would I have had to take the derivative of to get 2x? And it would be x squared, and that's okay. Now, what if it had said 3x? That wouldn't have been all that friendly, right?
No.
I mean, 2x was friendly, 3x not so friendly.
3 divided by 3.
So the other option of how you can think about this is that there's an exponent of 1, correct?
Yeah.
So if I increase that exponent by 1, I would get an exponent now of
2.
2. And the power rule says that new exponent will be the divisor.
So it's 2 over 2.
Yeah, and then this 2 at the beginning, that's the constant multiplier rule. And then, of course, those 2's cancel. Okay? And that's how we can think about the next one as well. So let's think about it from that perspective instead of from the, what would this have been the derivative of perspective. So the 3 is going to stay because it's a constant multiplier. X squared, I need to increase the exponent by 1, which gives me x cubed. And I divide by the new exponent. And then, of course, in this one, the 3's also cancel. So this gives me x cubed.
Plus C.
Thank you, plus c. Now you'll notice I did not write down capital Y equals or capital F of x equals or anything like that, right? Why didn't I need to? I wrote an equals because on the left-hand side I had the integral notation. Do you see the script s at the beginning and the dx at the end?
And
Yep.
minus x squared.
Oh, I'm sorry. That's why several of you are looking at me funny, I think. I got my sign wrong. Thank you. Okay. Is that okay now?
He's asking what the dx is.
Yeah, so this, I'm sorry, I didn't actually talk to you guys about that. This right here, these notations always go together. The s at the beginning means antiderivative, okay? The dx at the end means that's the variable that's used in the problem, dx. Okay, so dx is telling you with respect to x, okay? So in theory, x is not the only letter we could use as a variable, right?
Yeah.
Yeah, you'll see t used a lot as well, so you might see a dt at the end. When we get further along into chapter 4, you're going to see some u's, so you're going to see a du at the end. All right, so it's just telling you this is the variable in my problem. These two go together. They are either both present or they're both absent. So if you have one and not the other, you've got a mistake. All right, let's take a look at the second one. Oops. All right. Now you might notice this and say, okay, well there's an x to the 6th, then just start working with it as though it's x to the 6th, and you cannot do that. It needs to look like one of the rules we already have. In particular, it means we might need to rewrite something. So how could I rewrite this to look more like something I already have?
X to the negative 6.
X to the negative 6. I still have the minus 2 at the end. I still have a dx at the end and the script s at the beginning. So this piece is a power rule, agreed? Okay, so I take the exponent, which is negative 6, and what do I do to it?
You have to raise
Plus
the
1.
power.
I raise the power by 1, which gives me what?
Negative.
Negative 5.
Negative 5. So this will be x to the negative 5. What do I do next?
Divided by negative 5.
Divide by that new power, negative 5, and then I'm done with that piece. Now the next piece we haven't seen happen directly yet. We talked about it, but what would I have to do to negative 2? Okay, and I want to be careful because I don't want to really add an x. I think you mean attach an x or something like that, right? Yeah. So we will attach an x, multiply by an x, include an x onto the 2. And again, if you think about it, the reason is because 2x's derivative is 2. So if you think about going backwards, that's what would work. Okay?
Plus C.
And then I need a plus c. Now, we have two things to discuss at this point. Very soon, we'll see how soon actually, because then that's awfully generic. Very soon. Very soon is in the 18th. That would be a week from Friday.
Oh,
You
wow.
will be doing a quiz in class. Similar to one you've already done before called a gateway quiz or a basic skills quiz, whatever I called it in your skills or in your syllabus. And if you were doing that quiz, you would stop this problem right here.
Oh, sweet.
Okay? You'd do no more simplification.
There's more to do.
Nothing. Yes, there is something else we're going to do in this problem.
Oh, that.
So then the question becomes, well, then what simplification would I need to do? Well, you need the problem to look like it started. This problem, as it began, had no negative exponents, correct? So when the problem ends, it also should have no negative exponents. So how do I rewrite this so that that negative exponent, x to the negative 5 part, isn't there? Yeah, I need to move it to the bottom. So I would still have a 1 on top. I can still have the negative 5 on bottom, or if you want to put the negative in front, that's okay. But I will have an x to the 5th on bottom minus the 2x plus c. I don't know if WebAssign is going to make you do that or not, but I will assure you that when it comes to a test or a quiz or a homework assignment you turn in, I would expect that you would do it. Okay, the problem just needs to look like it began. The answer look like it began. Any questions on that one?
So if we took the derivative that we would get the top.
Yes, you would. Now, it'd be easier to take it in this form, right? If you had it written in that middle form and you took the derivative.
Yeah.
Check it out. What's the derivative of x to the negative 5? Well, you bring the negative 5 down, which would cancel with the negative 5 in the denominator. You decrease the exponent by 1, which would make it negative 6. Okay? And the derivative of negative 2x should be negative 2. So, yeah, so in a very real sense, you do not need a back of the book on these problems. You guys with me? You should be able to check your own work very quickly because it's actually what you've been doing now for 2 months, taking derivatives. And what we're doing right now with the antiderivatives is the simple antiderivative stuff. It's not complicated chain rule, product rule. You're not going to need anything like that, okay? It's going to be simple antiderivatives.
Will there be harder ones?
Yeah, in Calc 2.
Okay.
Yeah, in Calc 2. There's going to be a little bit harder as we get toward the end of Chapter 4, but when we get toward the end of Chapter 4, for those of you who have had some calculus before, we'll be doing U substitution. That's as far as we go in Calc 1. Okay. All right. This does not look like any rule that we just wrote down, but it can be changed to look like some. So what would I need to do to change this expression as it's written currently? All right. This x, the first x, is x to the 1. The second piece is x to the 1/2. So how can I combine those? Because it's a product rule right now. And then I'm going to have a product rule. Yeah, we add exponents. So this is 1 over x to the 3/2. I need one more change of form before I can actually use my rules.
Negative 3/2.
Yeah, I need to move it up. So I'll write this as x to the negative 3/2. In this form, it actually looks like one of my rules. So you keep manipulating until it can use one of the appropriate manipulating. Don't go doing things that aren't allowed. That's not going to help you. But yeah, you got to keep changing it until it actually fits within one of the rules that you've got. Can we do this one?
Yeah.
Of course you can. You can take that exponent, and what do you have to do to it?
1/2. The 1/2.
Add 1. So if you take negative 3/2 and you add 1, you get negative 1/2. Okay? I know some of you probably don't like fractions, but we're not going to do too much with them, okay? We do need to divide by that new exponent, agreed? This looks and feels a bit funny, but I'm going to write it this way for now anyway. Divide by negative 1/2.
Okay.
What else do we need to do? Plus c. And on the gateway, you would stop there.
Okay.
On your homework, you would not, for a couple of reasons. Number one, you don't get to leave anything in dividing by a fraction form. That's not cool. Like that's not cool way back to high school, not cool, right? Yeah. And while there's really nothing wrong with negative exponents, we're not going to leave it in that form because the original problem didn't start out in that form. Number one, it didn't have negatives, and number two, it didn't even have exponents, correct? So we need to change that back into the form that it should look like. Let's deal with the x or the denominator first. What is the same as dividing by negative 1/2?
2.
Multiplying by negative 2. So I'm going to rewrite this as multiplying by negative 2, right? Dividing by a value is the same as multiplying by the reciprocal, and the reciprocal of negative 1/2 would be negative 2. What's that? Yeah, okay, and then we're going to have to move that x to the negative 1/2 down. So now it'll be a positive 1/2, and a positive 1/2 is the same as a square root. So I have negative 2 over the square root of x plus c. Okay, Christian.
Okay, this is going to sound really stupid, but can you not just multiply everything by 2?
What do you mean multiply everything by 2? Where? Where are you looking at?
Like the step right above the bottom.
Right here, like to simplify it? Yeah, you can. It's the same thing. If you did that, it would eliminate your denominator to give you that 2. I'd still have the negative, and it would still give me a negative 2 on the numerator or out in front of the fraction.
Okay.
It's the same idea.
All right.
Yes, also works, absolutely.
You wouldn't have to write like QC because it would still be just like a number.
That's a good question. Yeah, we don't need to ever multiply or add or subtract or do anything with C because C is an arbitrary constant anyway. So really, if you multiply C by 2, you're going to get just another constant, and so we don't care what kind of, I mean, we have no idea what it is anyway, so it doesn't matter. Yep. Okay, number 4. Number 4 looks like I've got multiplication in the problem. And when you know, because you told me, there is no product rule that we've been dealing with yet. So we need to FOIL this out to start with. Okay, algebra here. Got to do some algebra. You guys are getting so good at algebra. Aren't you so excited about that? I know you are. You were just like, man, algebra was the bane of my existence, and now you know how to do it just fine. All right, so as we're FOILing this out, we get 3x squared. The inside gives me 3, and the outside gives me negative 2, giving me a total of what?
Plus 2, plus x.
Plus x.
Minus 2.
And then my last term, yes, is minus 2.
Go, go, go.
dx. Please, please remember your dx. I am going to be mean about that. So make sure it's on there. It's like the limit stuff, right? You don't take it off until you actually put the number in. You don't take this off until you actually take the antiderivative. 3x squared. Well, the 3 would stay. I would increase my exponent by 1 and divide by new exponent. So what am I going to do with x?
It's 1/2 x.
Okay, so I'm going to increase the exponent to 2, and then I'm going to divide it by 2, which is the same as multiplying by 1/2, and you can write it that way if you like it better. What about my negative 2?
Negative
Negative
2.
2x.
Negative 2x, and then plus c. You can leave it like this on a gateway. On the actual quiz or test or exam or whatever, we would simplify the 3's, of course, at the beginning. And our final answer would say x cubed. You can write this as x squared over 2, or as Garrett mentioned, you could also write it as 1/2 x squared if you'd like that better, minus the 2x plus c. So divided by 2 or multiplied by the 1/2 is the same answer. Okay, are we good? All right, because now we need some trig, because we haven't done any. Okay, the first piece, what is the antiderivative of 1?
X.
Good. How about the antiderivative of negative cosecant x cotangent x?
Cotangent.
It is cosecant x. Is it going to be positive or negative? It's going to be positive because there's already a negative here. And again, what you can think about is the derivative of cosecant x is negative cosecant cotangent, which is what's in my problem,
Plus c.
plus a c. And then we're done.
What's up?
Okay, I've got like 4 of you texting, so if you'd put those away because it's distracting me, I'd really appreciate it. All right, next problem. I've got sine over 1 minus sine squared x. This makes things a little bit tricky because there's subtraction in the denominator. So you could split it, Garrett, if the subtraction were in the numerator, but it's not. So I need to do something else in that denominator to write it differently.
Break it apart.
Okay, so say that louder for me, Luke, so everybody hears you. Okay, that was only like tiny. I'm not sure that was louder at all, actually. I was about to give you the benefit of the doubt, but I'm not sure.
Can you put cosine squared x?
Thank you so much. Yes, you can. So why can you do that? Somebody verify to me why you can do that.
I remember that part at least.
It's a property from trig, and it was called a Pythagorean identity, right? And so if you are forgetting those would be really helpful for you to remember along about right now. Okay, so I have a paper, a sheet inside of Moodle Rooms you can print off. There's basically 3 types of trig identities that are useful to like completely remind yourself of every time, not revamp, but remind yourself of. Pythagorean identities, reciprocal identities, and quotient identities. Those are the 3. And they're the top 3 on that trig sheet inside of Moodle Rooms. This is the Pythagorean identity. And it says that sine squared plus cosine squared equals 1. So if we manipulate that, we can also see then that the bottom is actually cosine of x. Squared. Sorry, my squared's missing. I was like, something's wrong with that. There we go. That's better. Cosine squared of x. So that's cool, but somehow that still doesn't quite look like a helpful piece of information. So I'm going to do something that Garrett asked me to do, but he didn't ask me to do it here, and I'm going to split this up. Cosine squared is the same as cosine times cosine, right?
Tangent.
Yeah. Well, okay, yes. 1 second on that.
Okay.
I'm going to rewrite this as cosine of x times cosine of x. Okay? And in fact, not only am I going to do that, but I'm going to sort of split this apart like it's two fractions. Can I do that?
Why not? Sure.
Yeah, I'm allowed to do that. It's all multiplication. Addition and subtraction, I can't do that, but multiplication is totally totally possible. All right, so Mooney, you already spoiled the fun, and you already said what sine over cosine is, so say it again for me.
Tangent.
Tangent. That's useful. Now, what about that 1 over cosine? It is one of the ones in the sheet, you're right. It is secant, you're right.
Oh, it's cosecant?
It is secant. Yeah, so I think, after Friday's test, probably everybody needs to print that out and take a look back at those so that they have that with them as they're looking. 1 over cosine is secant.
It's not even like the antiderivative. We just literally rewrote the thing.
We literally rewrote the thing with trig identities. That's exactly right.
I don't like trig.
We're not even to the calculus yet. That's right. But now it's one we know. You're exactly right. Whose antiderivative would be tangent secant? I'm sorry, whose derivative would be tangent secant? Secant. So the antiderivative here is secant of x plus c. That's insane. All of those steps to get back to secant, it didn't look anything like it started, right?
No.
Manipulation of trig. Who knew that that would be useful?
Why would they write
Probably
the
some
derivative
trig
like
teacher
that?
somewhere told you this would
Why
be
would
useful.
you use that derivative?
Yeah, why would they write the
Just make it tangent secant.
I get lost.
Life's simpler.
We're going to do
that way.
applications of, I think it's in this chapter. We're going to do some applications, yeah, it is, of these functions.
I
So
like tangent.
right now we're just learning how to do them, okay?
Okay.
No more trig.
You don't know that. Oh, Carrot.
No more
Why
trig.
would they write the derivative that way?
No more trig.
They wouldn't write the derivative that way. They're starting with something where they created a function and they're asking you to find the antiderivative.
No more
We just
trig.
keep asking ourselves about derivatives because it's a prior knowledge that's easy for us to access. That's why. Yeah. It's kind of like, do you guys remember proving trig identities in trig? It's like the thing everybody hates the most. You guys know what I'm talking about?
Yeah, I remember.
And it's really tricky because they'd start in one obscure place and they'd have to prove something else to another obscure place, right?
Yeah.
This is kind of why you did it. Not kind of, actually, is exactly why you did that. Is because you've started in some weird place and you've done a manipulation of something to get it to be something you know and can use.
Yeah.
Okay? All right, we have a couple more examples. I'm going to show you. This one says we're going to find the particular solution that satisfies the differential equation and the initial condition. And oh my goodness, that does not sound like anything we just talked about, right? Okay? So first of all, it actually is something you talked about, and you can kind of identify it based on the function that you're given. F prime of x equals 4x squared. So when it says to find the particular solution, it's asking you to find the antiderivative. Okay? Now, this is called a differential equation because it's a derivative equation. Does that make sense? Sure. And then the initial condition right here is going to allow us to find c. Okay? So we're going to do the same thing we already did, except that in the end, we're going to actually be able to solve for what c is. So this says f prime of x. So I'm going to be first finding the antiderivative of 4x squared dx. So what am I going to do to find the antiderivative of 4x squared?
Raise the power, divide by.
Raise the power, divide by that power. You got it. And then I need to put plus c. And this will have the name f of x because it actually called it f prime to start with. So I'm not capitalizing here because they actually gave it to me in derivative form f prime to begin with. Now, the other information that's sort of all glossed over because I messed it up over here that they give us that's useful and needful now is that f prime of negative 1 equals 3. So, I'm sorry, not prime, f of negative 1 equals 3. So what they're saying is that if I take this equation and I plug in negative 1 to it, so I have negative 1 cubed over 3 plus c, that this is going to equal 3.
Oh my gosh.
So my goal is to simply figure out what c has to be to make that true, right? All right, so what am I going to get out of the 4 times negative 1 cubed over 3?
-4/3.
That is negative 4/3 plus c. Oops. And then that equals 3. So if we keep going, then I would add the 4/3 to the right-hand side. So what is 3 plus 4/3?
14.
It's what?
14 over 3. No,
It's 13, right?
13. Oh.
13 over 3. This one would be 9 over 3, and 9 plus 4 is 13.
Okay.
Because c is 13 over 3. You're not done. What they ask you to do is to actually find the solution, which means to take what you got here and plug it in for c. So f of x equals 4/3 x cubed plus 13 over 3. One last question. Same idea. They want us to find the particular solution that satisfies the differential equation and has the initial condition, but what they give you is the second derivative. Y'all see that? Okay, but if I take an antiderivative of the second derivative, where do you think that leaves me? At the derivative. I'm just going backwards, right? So if I started with the second, I'll go back to the first. What's the antiderivative of x squared? Yeah, 1/3 x cubed, or x cubed over 3, plus c. And they give us a fantastic piece of information here that says that f prime of 0 equals 8. So I can use that. F prime of 0. 0 cubed over 3 plus c equals 8. What is c?
8.
8. So now I know that f prime of x equals x cubed over 3, or 1/3 x cubed, plus 8. Was that what I was supposed to find?
No.
Not yet. I'm not finished. I have another piece of information about f, and I want the particular solution, which means the original f of x equation. So I do it again.
That doesn't really. Why did they make you do that? It doesn't.
Well, we're finding the f of x function. They gave you the second derivative instead of giving you the first derivatives to start with.
Yeah, but like, why did they make you find what c?
Because if you're actually needing to evaluate the function, you would need to know what the c value is to make it useful. When you actually have a plus c on the end, it gives you the basic shape of the function, but it means it can be shifted up and down wherever it is on the curve. All right, we're almost done. Let's finish real quick. This is f of x on the left. What do I get with the 1/3 x cubed on the right?
12.
1/12 x.
1/12.
1/12 x to the fourth, because it'd be x to the fourth over
Plus
4,
8x.
plus my 8x,
Plus C.
plus c. Can I find c?
Yes.
Yes, I can, because they tell me f of 0 equals 4. So this is 1/12, 0 to the fourth, plus 8 times 0,
0.
plus c equals 4. So on this one, c is equal to 4, and my actual function is what? 1/12
1/12
x to the fourth
plus 8x
plus 8x plus 4. And if we were to take the derivative of this and then take the derivative of that, would we get back to x squared?
Yes.
We would. We would. All right.